We want to graph this rational function f of x equals x squared minus 4x plus 4 divided by x plus 3. So we will begin with the function's domain. So because this is a rational function, and that means that it's a fraction, we know we can't have 0 in the denominator of a fraction. So we'll be looking at the denominator and seeing what would cause the denominator to equal 0. So in this case, we know that x cannot equal negative 3. If x were to equal negative 3, we would have 0 in the denominator, division by 0. So our domain is going to be all values of x such that x cannot equal negative 3. That's set notation, and I'll go ahead and write it in interval notation as well, negative infinity to negative 3, unioned with negative 3 to infinity. And the one benefit of using interval notation instead of set notation is you can kind of see that you have two intervals, so we're going to have two pieces on our graph, or we're going to have two sections, two branches. That'll become a little more obvious later on. So after the domain, we move on to the vertical asymptotes. Now, to determine your vertical asymptotes, remember we want to simplify the function first. So that means we want to come back here and see if this function factors and possibly simplifies. So if we were to factor the numerator, it'll factor into x minus 2 times x minus 2, or in this case, x minus 2, the quantity squared, divided by x plus 3. So it turns out we don't have any simplifying that can occur. So the vertical asymptotes are going to be where the function is undefined, and we know that it would be undefined when x is equal to negative 3. So x equals negative 3 is our vertical asymptote. Remember again, it's so important that you do write x equals negative 3, because if you just have negative 3, that's just a number, that's not actually a line. And this asymptote is a line. It's this imaginary vertical line, if you can think of it like that, that the graph is going to get very, very close to, but not touch. So as always, I recommend that you graph as you go. So I would go ahead and plot this vertical asymptote as soon as you find it. I like to do my asymptotes in a different color. So here's this imaginary vertical line that my graph is going to get very, very close to. But remember, these graphs can never cross through their vertical asymptotes because the vertical asymptote is where that function was undefined. So we can't cross through those vertical asymptotes. Now we move on to the horizontal asymptote, which is going to depend on the degree of the numerator and the denominator. So looking back at the original function, you see that we had a degree of 2 in the numerator, and then the denominator was x here raised to the first power, or a degree of 1. So the degree of the numerator is greater than the degree of the denominator, which tells us that we do not have a horizontal asymptote in this case. So no horizontal asymptote. But we do know that the degree of the numerator is exactly 1 greater than the degree of the denominator. So that tells us that we have a slant asymptote, also called an oblique asymptote, if you prefer that term. Instead of slant, oblique, they're interchangeable. So we need to do division to figure out what our slant asymptote is. So you have two options. You can choose to do long division and divide x plus 3 into x squared minus 4x plus 4. We're just taking the original rational function and we're just doing the division. Or if you recognize that what we're dividing by, the divisor here, x plus 3 is linear, then we could make use of synthetic division instead. That would certainly be my choice. I'm only going to do long division if I absolutely have to. So I'm going to choose to do synthetic division. So that means that because I'm dividing by x plus 3, I'll have negative 3 out in the box. And my coefficients are 1, negative 4, and 4. Remember, you would need to include a 0 if you were missing a term. So synthetically divide, bring down the 1, multiply by the negative 3, and then add, and multiply, and add. So 25 would be my remainder, but the remainder is insignificant in this case because the slant asymptote is just impacting the far ends of the graph as x gets really, really big and really, really small. So we're really only interested in the 1 and the negative 7, which would represent the line, oops, I'm out of room, sorry about that, I'll come over here to the side and then erase it in a second. The line would be y equals x minus 7. So this would be the equation for my slant asymptote. Now, to graph this slant asymptote, remember, this is just a line in slope-intercept form. Think of it as y equals mx plus b. So we know that we have a slope of positive 1, and then the y-intercept for this line, this slant asymptote, is negative 7, which immediately I was seeing on my graph, I did not have enough room. So I'm going to go ahead and go to a new page and create a bigger graph. So to graph that slant asymptote, I have a y-intercept of negative 7, and then my slope is positive 1. So again, I'm graphing this as if it is just a regular line, but I am doing it in red. So I'm just graphing that y-intercept of negative 7 and my slope of positive 1. And now I can come in here and create that asymptote. A straight edge would be a good idea as well. So this is going to be my slant asymptote. All right, going back then to our list. We've got our asymptotes, and now we can move on to some points on the graph. So let's go ahead and take a look at the x-intercepts. So we know to find x-intercepts, we're going to let y equal 0. So if I let y equal 0, we could use the original graph here, we could use the factored form, either one. I kind of like the factored form. I might as well go ahead and use that. So 0 is equal to x minus 2 squared divided by x plus 3. So first order of business here is we need to eliminate this division by x plus 3. So you think about multiplying both sides of the equation by x plus 3 to eliminate this division. But on the left-hand side, 0 times x plus 3 is going to be just 0. And that's why in a lot of textbooks you might read in this section where they find the x-intercepts, they say, oh, you're just going to set the numerator equal to 0. Well, the reason for that is, of course, because when we're having our division and undoing the division with multiplication, then the denominator is always going to go away and we're always left with just the numerator. So we're solving 0 is equal to x minus 2, the quantity squared, which we can square root both sides. And we'll have x minus 2 is equal to 0, so x is equal to 2. So our x-intercept is 2. But it is worth noting here that that was x minus 2, the quantity squared. So we technically have a multiplicity here. Just like we had our discussion of multiplicities with polynomial functions, we can apply that to our new study of rational functions. It's still going to apply. So because that was an x minus 2 squared, we have a multiplicity. So I'm going to write multiplicity of 2, which, remember, anytime we had that even multiplicity, that meant that the graph was going to touch the x-axis at 2. And that's worth noting. And then our last point for now is going to be that y-intercept. So we're going to substitute 0 for x. And again, we could do that in the original or in the factored form, either one. Doesn't matter, I tend to go back to the original. 0 squared minus 4 times 0 plus 4, all divided by 0 plus 3. And you can see that our y-intercept is going to be 4/3, or you could rewrite that as 1 and 1/3. We know that that's really 1 and 1/3. That'll help us actually graph it. All right, so now let's go ahead and graph the x-intercept as well as the y-intercept and put everything together. So we have our x-intercept, which is at positive 2. And then we have our y-intercept, which is 1 and 1/3. And those are the only 2 points that we have right now on our curve. But we do know that the graph is going to touch the x-axis at positive 2. So we could go ahead and actually begin the branch that we're going to have here, because we know, there it is, that it's going to hug that asymptote. It's going to come across your y-axis, it's going to just touch, and then it's going to come over here and cruise along that slant asymptote. But it is worth checking to see right up here, question mark, is the branch here going to cross the slant asymptote? So if you wanted to answer that question, we would have to do a little bit of algebra first. Will f of x cross the slant asymptote? Well, if it's going to cross the slant asymptote, then that means that there's a place where the function is equal to the slant asymptote, which basically means if you take the original function, x squared minus 4x plus 4 divided by x plus 3, then we're questioning, is there a place where this graph would equal the slant asymptote, which was y equals x minus 7. So we're essentially just setting these two expressions equal to one another, and then we have an equation now that we can solve. So we would solve by multiplying both sides of our equation by x plus 3 to eliminate the division. So both the right and left hand sides. We multiply, we'll get rid of that division here on the left hand side. So that leaves us with x squared minus 4x plus 4. And if you go ahead and multiply, distribute the right hand side, you'd have x squared minus 4x minus 21. So if we begin to move terms, we'll subtract x squared. You notice that the x squareds will subtract out completely. And if you add 4x to both sides, you notice the same thing occurs for the 4x's. So what we're left with right now is the statement 4 is equal to negative 21, which is certainly not true. So because we're not getting a solution here, this is not a true statement, then now we've answered the question. The question's answer is no, the function will not cross its slant asymptote. So if we go back to our graph, now we can say without a doubt, we know that this branch is going to just continue to cruise along and just hug that slant asymptote and get very, very close to it, but it's never going to actually intersect the slant asymptote. Now, be careful, because if you're in a hurry, you might think that you're done. But if you go back, all the way back here to our original domain, remember how I said if you would write the domain in interval notation, you'll see that you have two intervals. And that's a signal to tell you that we're going to have two branches on our graph. And that means that we have to have something happening over here to the left of that vertical asymptote. So I need another piece. I'm missing a piece right now, and I'm not sure where that piece is. So there's two different ways of figuring out where the other branch lies. And one way is just with logic, and one way is by actually plotting some points. So let me start you with the logic, because I prefer that myself. So you think about what it might look like, and I'll do this in a different color. Because this is not necessarily what the branch looks like, but this is what it possibly could look like. We know that the branch has to approach and get very close to the vertical asymptote. Try again. All right, here we go. There we go. So it could go up like this and then come down, and then again it has to cruise along the slant asymptote. You could have something that looks like that. That's one option. Another option is that there's this little tiny area in this little corner, I should say. So you could have kind of this little U-shaped branch down here. That's another option, okay? Now, you cannot have both of these branches because the function would not pass the vertical line test, and it wouldn't be a function. So you have to have one or the other. So let's say that you had the long one here. If this was the accurate graph, then notice that you would have an additional x-intercept. That this green branch would cross the x-axis, it would cross it one more time right here, and we would have another x-intercept. But if you go back and take a look at our work, we found that the x-intercept was positive 2. That was the only x-intercept on this entire graph. So by using a little logic and realizing I cannot have another x-intercept, this tells you that you cannot have a green branch that looks like this, that our branch has to be down below. Okay, so that means that the branch would have to be down here in this little lower region. Something like that. It's kind of small. With you have a bigger graph, you'll be able to fit it in. Okay, so that's using logic to figure out where the other piece has to lie. The other way of getting an exact point, which is sometimes necessary, is just to kind of go back to what I call old school and make a table. You just have to plot an additional point. So because our vertical asymptote was at x equals negative 3, then a good value to plug in would go to the left of that point, or left of that line, which would be x equals negative 4, and we're going to go ahead and just plug and chug, if you will. We're going to substitute negative 4 into the original function. In other words, you need to find f of negative 4. So that original function was x squared, that would be negative 4 squared, minus 4 times negative 4, plus 4, sorry, not letting me write a 4 there, all divided by negative 4 plus 3. And you might be asking, could I have done this in the factored form? Certainly, absolutely. You'll get 16 plus 16 plus 4, all divided by negative 1. And that would be 32 plus 4, or 36, divided by negative 1. You'll see that my y value is negative 36. So then if you had counted all the way down, you'd actually see, okay, way down here at negative 36, that would have been my y value at negative 4, which supports that I do have this correct little branch here. This little green branch is in the correct location. And there you have it. That's the graph of a rational function that has a slant asymptote.